Today, we are looking at a paper called The Flexibility Trap: Why Arbitrary Order Limits Reasoning Potential in Diffusion Language Models. It's from Zhanlin Ni and the team at Leap Lab, Tsinghua University, and Alibaba Group.
And this paper is a serious reality check for a lot of folks in the generative AI community. We've seen this huge surge in interest around diffusion LLMs or dLLMs.
Right.
And it's specifically because they promise to break that strict left-to-right generation constraint of, your standard models. The theory was that arbitrary order thinking in any direction would unlock really superior reasoning.
But this research shows the exact opposite. It turns out that flexibility is, well, it's a trap. When you give a model the freedom to generate tokens in any order, it avoids the hard work.
Yeah.
It skips over these high uncertainty forking tokens, logical words like therefore or since, and that causes what the authors call entropy degradation. The model's whole solution space just collapses. It gets dumber.
But they do propose a fix, and it's incredibly effective, but also really counterintuitive. It's called JustGRPO. The idea is you force the diffusion model to behave like a standard autoregressive model, but only during the reinforcement learning phase.
Okay, so just during training.
Just during training. And by forcing it to think linearly then, they got state-of-the-art results, like 89.1% on GSM-8K, and they still got to keep all the parallel decoding speed benefits of diffusion when it's time for inference.
That's the 1-minute snapshot.
Okay.
Now, let's really get into it, because if you're out there building these models, this paper basically rewrites the playbook on how to train them.
Oh, really does. To see why this is such a big deal, you have to look at the landscape. On one side, you have the incumbents, autoregressive models, your GPT-4s, your llamas.
Left to right, strictly linear.
Exactly. Causal. Token dollars is generated based on everything that came before it. And then you have the challengers. Diffusion LLMs. They're inspired by, all the success diffusion has had in image generation.
Right. They start with noise and kind of refine it into text.
Precisely. Instead of one token at a time, they denoise a whole sequence iteratively.
And the big sales pitch for dLLMs has always been two things. First, speed. You're not stuck generating one token at a time, so you can do parallel decoding. Generate half a sentence at once.
Right. A massive speed up for inference. But the second selling point, and this is the one the paper just dismantles, is this supposed reasoning advantage of arbitrary order.
And the intuition there is really seductive, isn't it?
Yeah.
I mean, when I solve a problem, I don't always think in a straight line. I might jump to the conclusion, write that down, and then work my way backward.
That's it. It feels like if a model can generate in any order, it should just be smarter.
This is what they call the Superset Hypothesis, right?
Exactly. The researchers lay it out really clearly. The set of all possible arbitrary generation orders technically includes the strict left-to-right order as just one tiny subset. So logically, you'd think a model that can explore that entire superset.
It should be able to find solutions that a linear-only model just can't. It has a superpower. It can choose to be linear if that's best, or nonlinear if that's better.
That was the hope. But the authors of this paper decided to stop hypothesizing and actually measure it. And they used a metric called pass at k to test the reasoning boundaries of these models.
And for anyone not familiar, pass at k basically asks, if we let the model generate, say, 100 different solutions, what's the probability that at least one of them is correct? It's a measure of the solution space.
Exactly. It's asking, can the model find the answer at all, given enough tries? And this is where the whole superset hypothesis just falls apart.
What did they do?
They took a standard diffusion LLM and ran 2 experiments. In one, they let it use its fancy arbitrary order generation. In the other, they constrained it to generate tokens strictly left to right, like a GPT.
And the results were not great for the flexible approach.
They were brutal. When they forced the model to be linear, it achieved a significantly higher reasoning boundary. On the human evil coding benchmark, they found that 21.3% of the problems were solved only when using the strict autoregressive order.
And how many were solved exclusively by the flexible arbitrary order?
0.6%.
Wow. So statistically nothing.
It's noise. It basically means that this superpower gives you no real advantage, and in fact, it actively hurts performance. The flexible model wasn't finding new, creative ways to write code. It was just retreating into a smaller, less effective corner of the solution space.
Okay, so the question for any researcher listening is just why? Why does giving a model more freedom to think lead to worse results? And this gets us to the core technical idea in the paper: entropy degradation.
This part is fascinating. You have to think about how a diffusion model chooses what to generate next. In arbitrary order mode, it can pick which token to denoise first. It looks at the whole noisy sequence and it asks, what am I most confident about?
It hunts for low entropy. The easy wins.
Correct. It looks for the tokens where the probability distribution is really sharp. And the authors introduce this concept of forking tokens here, which I think is a brilliant way to visualize it.
Right.
In any logical chain, a math proof, or a piece of code, there are these critical decision points, and they identify them as logical connectors. Therefore, thus, since, however,
These are the moments where the reasoning path literally branches. Before you write therefore, you have to decide on the conclusion. It's a fork in the road, so the uncertainty, the entropy, is naturally high. There are multiple ways you could go.
in a standard autoregressive model, the model is handcuffed. It reaches that word, therefore, and it has no choice but to sample from that high entropy distribution. It is forced to make a decision.
It has to confront the uncertainty.
Yes, it forces exploration. It might pick the wrong path, but it explores a path. Now, contrast that with the arbitrary order diffusion model. The diffusion model sees that high entropy, therefore, and says, too risky, I'm not touching that yet. Instead, it looks ahead. It sees the end of the sentence. Maybe it's just a closing bracket or a variable that was already defined. Those are low entropy, easy.
So it generates the easy ending first.
Exactly.
Yeah.
It fills in the end of the proofs before it has even established the logic. But here's the trap. Once those future tokens are generated, they become part of the context for everything else.
So by writing the ending, it has collapsed all the possibilities for what could have come before it.
You nailed it. By the time the model circles back to finally fill in that therefore, the decision has already been made for it by the surrounding context. The high entropy is gone. The fork in the road has vanished.
This is entropy degradation.
That's it. The authors actually measured this. In AR mode, the entropy spikes at these logical connectors. You can see the model thinking. In arbitrary order mode, the entropy is just flat. The model isn't making a logical choice. It's just filling in a blank to be grammatically consistent with an ending it already wrote.
It's cheating. It's like a student who looks at the answers in the back of the book, writes that down, and then just tries to sudge the work to get there. They finished the problem, but they didn't actually reason through it.
And just like that student, when the problem gets really hard, when you can't guess the answer, the model fails. It trades that deep exploration for just local consistency.
This makes so much sense. But the paper goes further. It argues this flexibility doesn't just hurt reasoning. It actually makes training these things a complete nightmare.
Oh, the training side of this is so messy. I mean, if you're an ML engineer trying to use reinforcement learning on a diffusion model, you're probably just banging your head against a wall.
Because RL needs you to calculate the probability of a given trajectory, right?
Right. And in an AR model, there's only one trajectory, left to right. The math is clean. But if you want to support arbitrary order, you theoretically have to account for every possible order the tokens could be generated in.
Which is a factorial explosion. No dollar factorial.
It's completely intractable. So what researchers have been doing is using approximations, ELLBO-based surrogates, trying to estimate importance ratios.
And approximations always introduce noise.
Huge amounts of it. You get high variance gradients, this sampler-learner mismatch. The RL algorithm just struggles to figure out which actions actually led to the right answer because the exploration is so chaotic.
We're paying this huge flexibility tax using unstable, noisy math to preserve a feature arbitrary order that we just proved is bad for reasoning in the first place.
Exactly. It's a lose-lose, and that's what makes their solution so elegant.
This is where JustGRPO comes in.
The name says it all, really. Just use GRPO.
For a bit of context, GRPO is Group Relative Policy Optimization. It's a standard, stable RL algorithm. It was used in models like DeepSeek math, but you can't normally apply it to dLLMs because of those likelihood issues we just talked about.
Right, so the authors propose this radical simplification. They just say, during the RL training phase, forget about arbitrary order. Just treat the diffusion model as if it were an autoregressive policy.
How do you do that technically? It's still a diffusion model under the hood.
You do it with masking. You set up your training batches so that for any token, the past, the left context is visible, but the future, the right context, is strictly masked out. You force the model to predict the next token based only on what came before.
You're putting training wheels on it, forcing it to be linear.
And because you do that, the likelihood of any sequence becomes exactly computable. No more marginalizing over null or factorial paths, no more ELBO surrogates. You can just use the standard probability chain rule, just like in a GKT.
So you turn this intractable, messy optimization problem into a standard, stable RL task.
And that stability really pays off. They compared JustGRPO against these complex, diffusion-specific RL methods like SPG and ESPO.
Which were designed specifically to handle all that messy, arbitrary order math.
And JustGRPO just crushed them. On GSM-8Pay, it hit 89.1% accuracy. The other methods were way behind. On Math 500, which is much harder, JustGRPO got 45.1%, beating the next best by over 6 percentage points.
That's a huge margin. We're usually fighting for 0.5%.
And it was faster to train. Because the math was exact, not approximate, the gradient estimates were low variance, so the model just converged much more quickly.
Okay, so this all makes sense. Force it to be linear during training, it learns better. But I can hear the question from the audience now. If we train it to be AR, doesn't it just become an AR model? Did we just build a really complicated, expensive llama?
This is maybe the most important takeaway for any engineers listening. And the answer is no. This is the magic trick of the paper.
Go on.
That AR constraint is only applied to the loss function and the masking during the RL update. The underlying neural network is still a diffusion transformer. It still learns to denoise. It still has all the conditional independence properties that make diffusion models special.
So at inference time, when we deploy it, we can take the training wheels off.
Yes. At inference time, you can go back to using parallel samplers, use the entropy-bounded sampler, generate multiple tokens at once. All that speed comes back.
But isn't train-test mismatch usually a bad thing? If I train it to be linear and then test it in parallel, shouldn't the performance just tank?
You would expect that, right? A distribution shift penalty. But they found the opposite. The JustGRPO trained model actually performed better with parallel decoding than the baseline models did.
So it's faster and smarter.
Yes. They have this really compelling chart where they crank up the parallelism, the number of tokens generated in each step. Normally, as you do that, accuracy plummets.
Right. Quality degrades as you speed up.
But with JustGRPO, the accuracy stayed incredibly robust. It maintained its reasoning power even at high speeds.
Why? What's the thinking there?
The hypothesis is that by forcing the model to confront uncertainty linearly during training, it learns a more robust reasoning manifold. It learns the true causal dependencies in the logic, A causes B causes C.
It builds a proper internal map of the logic instead of just surface-level patterns.
Exactly. So when you switch to parallel decoding at inference, the model isn't just guessing based on correlations. It's checking its guesses against that robust internal map. It allows the parallel sampler to be much more accurate because the underlying probability landscape is just cleaner.
It's like learning a piece of music. If you learn it note by note, slowly, perfectly in time, you internalize the structure. Then, when you perform, you can play it fast, you can even improvise. But if you just try to learn by smashing keys quickly from day one,
you just learn noise. You never learn the actual structure. The linear training builds the foundation. The parallel inference exploits it for speed.
That suggests the flexibility trap isn't just about order, but about the difficulty of the task. Linear generation is harder for the model because it can't cheat. And because it's harder, the learning signal is better.
Cheating is a real problem in RL. If an agent can find a loophole to get the reward without doing the actual task, it will. Arbitrary order was that loophole. JustGRPO closes it.
So let's zoom out. We've been hearing for a while that diffusion LLMs could be the next big architectural shift. Does a paper like this accelerate that?
I think it removes the single biggest roadblock. Until now, dLLMs were cool, but they always lagged AR models on hard reasoning tasks. People thought maybe that was just an inherent flaw in diffusion. This paper shows the issue wasn't the architecture. It was how we were training them.
We were just training them wrong.
We were training them on the wrong assumption, that flexibility is always better. Now that we know you can train them linearly with stable standard RL and still get the massive inference speed benefits, that's a very dangerous combination for the incumbents.
Right. If I can get GPT-4 level reasoning, but with parallel decoding that's 5 or 10 times faster, that completely changes the economics of serving these models.
Especially for things like agentic workflows or real-time code generation, where latency is everything. If JustGRPO scales up, we could see dLLMs become the standard for those kinds of applications.
So to make this really practical for the engineers listening, if there's working on non-autoregressive models, what should they do differently tomorrow?
Stop trying to solve the non-entactorial problem. Stop building these incredibly complex, approximated loss functions to support arbitrary order training. It's just not worth the effort.
Embrace the constraint.
Embrace the constraint. Mask your future tokens. Force the model to predict the next step linearly. Use standard GRPO. It's easier to implement, it converges faster, and the model it produces just reasons better. And then, once you have those weights, go nuts with parallel inference.
It's so rare in deep learning that the easier path is also the better one. Usually you have to pay for performance with a mountain of complexity.
It's Occam's razor, really. We assumed that complexity arbitrary order was necessary for intelligence. It turns out that a simple strict causality is the real foundation of it.
It's a fascinating pivot. We spent all this time trying to get AI to think outside the box of left to right text. Turns out the box is there for a reason.
The box forces you to commit, and commitment is the first step of reasoning.
That's a fantastic place to leave it. The paper is The Flexibility Trap, and it's up on our CUC-RL. If you're into the math of diffusion or RL, I'd really recommend the sections on the entropy measurements. The graphs are just so clear.
Oh, definitely. That comparison of the entropy profiles between AR and arbitrary order is one of those visualizations that just instantly clicks.
A huge thank you to the authors at Leap Lab, Tsinghua, and Alibaba for this work. It's really clarified a very murky part of the DLM landscape. And for our listeners, keep an eye on this space. If you see a sudden jump in the speed and quality of reasoning models in the next 6 months, you'll know JustGRPO probably had something to do with it.
Absolutely.
Thanks for tuning in. We'll catch you on the next look into the papers that matter.